Let's talk some more about grammars. That's what we started discussing last time. Today I want to talk about, among other things, grammars and sort of converting back and forth with NFA, DFA, and regular expression. Although we already know how to convert NFA, DFA, and regular expression amongst each other, really the question is how can we maybe convert those things on the right into a grammar, or maybe convert a grammar into one of those things on the right. Specifically, we should first of all ask if this is even possible. So, or maybe I should just refresh our memory about what grammars are like. You know, here's an example of a grammar. So those vertical lines mean or. This says S goes to AS or T, and T goes to BT or S or epsilon. Epsilon, as usual, means the empty string. Actually, I believe this grammar can generate any string. So this, if I call this G, here the language of G is actually AB star. That is, you can actually make any string you like using the rules from this grammar. Maybe let's try to derive, what I'm saying is we can derive actually any string. How about A, B, B, A? Can we do that? So you have to start with S. While I'm writing a specific derivation, we use that sort of double arrow. I want to make A, B, B, A. Well, to get the A first, I think, you look at this line here. It says the S can either turn into AS or it can turn into T. Question? My derivation, the last thing I'm going to do is to plug in that epsilon. Yeah, that's right. Well, that's not always the case, but in this case it is. So I'm going to do first S goes to AS because I want to end up with an A at the beginning. The next letter I want to see is a B. So in order to make a B, this S, first I will turn it into a T by using that first line there. S becomes T, so this is now AT. And then on the second line, I can make T becomes BT. So this is AT and then ABT. That was T goes to BT, right? The way I'm thinking this through is just looking sort of letter by letter, left to right. What do I want to produce next, and try to make it happen. So the next letter I want to produce is a B. I have a T there. A T can produce a B by doing this again. T goes to BT. So I'll go T goes to BT again. Makes it A, B, B, T now. And then the next letter, and actually the last letter I want to see is a little A. I have a T here. Oops. Supposed to be my dot. What should I do next for the purpose of making an A there? Yeah?
Put it back to S.
Yeah, T goes to S, and then I can do S goes to AS to make a A there. So T goes to S makes it A, B, B, S. And then that S goes to AS makes it A, B, B, A, S. Now, I have created all the little letters that I want. Remember the little letters? They are called the terminal symbols. The big letters are called the non-terminals. I want to finish off without generating any more letters. I can do S goes to T, and then T goes to epsilon, and we'll be done. So this becomes A, B, B, A, T, and then T goes to epsilon. A, B, B, A, and that's it. All right? This is a typical grammar derivation. This grammar, I believe you can make any string that you like, because just like no matter what this string was, in order from left to right, if you want to make an A, you use an S. If you want to make a B, you use T. And if you want to go back to making A's after you made some B's, you do this T goes to S, and you can go back and make some more A's. All right? Any questions about it? It's just refreshing our memory about what a grammar is and how it works. All right? Okay, let's talk about this point about can we convert back and forth from grammars and NFA, DFA regular expression. We should ask, first of all, if that even is that even theoretically possible? Every language you can get with NFA, DFA, or regular expression must be regular, right? But we saw last time actually some grammars give you languages which are non-regular. So that means, I suppose, one or the other direction here is not even going to be possible. Which way is not possible? Yeah. This way, he says, converting a grammar into a NFA, DFA regular expression, that is not always possible. Sometimes you can do it, like in that example you could, but in general, it is not always possible to go that way. So I'll try and write that. Some grammars make non-regular languages. For example, the standard example is this. S goes to ASB or epsilon. This generates the language A to the N, B to the N, which is not regular. And so this means, in general, you cannot expect to convert a grammar into a regular expression, or NFA, or DFA. Yeah.
Does it have to have an epsilon for the grammar to be a grammar?
No. Yeah, he asked, do you have to have epsilon somewhere? If you don't have any epsilons, you may be concerned if the grammar actually is possible to actually terminate in any final product. But it is possible without, for instance, if I do this, this one generates a to the n plus 1b to the n. It's basically the same, but at the end you end up with one extra a. So.
Actually, no. What I meant is that do you have to terminate it every time? Or you have a grammar that doesn't terminate, or it will S to AS?
Okay, yeah. How about this grammar, maybe?
It's just S.
With nothing else? Yeah, this one you keep on, if you do derivations, they just keep on making longer and longer strings, and you can never finish with anything. So that is technically allowed as a grammar. This is a legal grammar, but if this were G, the language of G here, anyone want to say? This would be all possible terminal strings that you can generate using the grammar. This is the empty set, because you cannot actually generate any string of terminal symbols, right? Any possible derivation that you do here will go on forever, and so there are no actual specific strings that you can generate with that grammar. So it is a legal grammar. It still counts as a grammar, but it's kind of useless. You would never actually encounter this grammar or use it for anything because it doesn't generate any terminal strings. All right. Anyway, yes, as I was saying, some grammars can generate non-regular languages. All right. What that means, this was sort of a little parenthetical. Actually, this second one is also non-regular. The empty set is a regular language because you can make a DFA which accepts no strings by just putting no accepting states. Anyway, what this means is, I will continue my remark up there. So, there can be no general procedure to convert any grammar to a NFA or DFA or regular expression. There can be no procedure to convert any grammar to NFA, DFA, regular expression, right? Because those things, NFA, DFA, regular expression, can only make regular languages. And so if you start with a non-regular language generated by a grammar, it's not going to be possible to convert it. But the other way maybe is possible. So is it possible to convert, say, let's just talk about NFAs, because all of those three categories are interchangeable with NFA. So let's just focus on NFAs. It is possible, though, and in fact, it's pretty easy. Like if you know the trick, you just have to remember how to do it. It is possible to convert NFA to grammar. And here's how you do it. So begin with an NFA. I will just make up an NFA, and I'm going to give letters, names to the states. I'll call the first one S for reasons which will become obvious. It's the starting state. And I'm just making this up. Let's say I have a B arrow like that, a B here, a A here, a comma epsilon here. All right, and let's say T is accepting. Yes?
This is
This is
an NFA.
an NFA, yeah. You can do the same thing on a DFA, because a DFA is also an NFA. So the idea here is each state of my NFA becomes a non-terminal symbol in the grammar. Each state becomes a non-terminal. And of course the starting state, just like I did here, becomes S, the starting symbol for the grammar. Whatever the starting state is, you better call that S in the grammar. And then the way you convert this to a grammar, I'll just show you how to do it, and then we'll try and talk about why this works. Each arrow gives you, each transition in the NFA makes a specific production in the grammar, which is what we call the arrows in the grammar. So the fact that there's an arrow from S to T means in the grammar I'm going to go S goes to AT. The fact that there's an arrow from T with a B back to itself is T goes to BT. So that, what I just wrote, is representing this looped edge back to itself. T goes to BT. Also, you can go T goes to R, labeled with a B. That's going to look like BR. Right? And for R, you just look at each of the outgoing arrows, and you copy them over in this way. R, there's an A arrow going back to R, so that you translate as R goes to AR. There's also an A arrow going over to S, which we translate as R goes to AS. And there's also an epsilon going over to S, which you translate as R goes to S. I mean, you could write epsilon S if you want, but epsilon, you don't need to put it in there because it represents the empty string. And there's one more ingredient that needs to be indicated in the grammar. Is this what you were going to ask?
I was thinking of what would give you a production where the non-terminal is first? Like how...
On the left side, you mean?
No, on the right side. Like it was flipped. Like you had like T
If you're doing this procedure in the way that I'm describing it, you would never use a production like that.
Okay.
So the way, if you are trying to translate an NFA into a grammar, you always put the non-terminal that's labeling the arrow followed by the destination state. What else do we need to indicate here? Yeah, the accepting states in the NFA. I have not done anything over here which represents which states are accepting. T is an accepting state. In terms of the grammar, I imagine that somehow represents like the end of the derivation, right? After you make it all the way through the whole string, you stop. And the way to do that in a grammar is like this. So that or epsilon right there, this represents the fact that T is an accepting state. And if there were other accepting states, I would put or epsilon wherever they appear in the grammar. All right? Yes?
The last one, R is to BS. The last one. This is a big one.
B?
Yeah, R to AR to AS to BS.
Not to BS.
Oh, epsilon.
Yeah, that's an epsilon. So yeah, you can write if you want epsilon S, but that's just S. Yeah.
Because I misread.
So the rule, if I were to say this sort of in words, each of the arrows in the NFA, each NFA transition if it was, you know, something like X, A, Y, like that in the NFA, this becomes the grammar production, X goes to AY, right? And the only other thing you need to know is the accepting states. If, say, X is accepting, also include X goes to epsilon, right? That's, I mean, this, I suppose you should just remember how to do this. This is how this little translation will work. Let's see, I don't know if you believe me, I mean, this is a very simple thing to do. You can just memorize the procedure and go through it, but maybe we can verify that this grammar down here is actually equivalent to this NFA up here. So let's imagine a string which is actually accepted on this NFA. I'm going to try and maybe I'll do a little copy paste in here so I don't have to scroll back and forth. Here's my NFA, and then I will put the grammar next to it. I want to convince ourselves that these are actually equivalent. So something that is accepted on the NFA accepts how about, I want something that's a little interesting. Let's go all the way around. So A, B, A, right? A, B, let's do an extra B just for fun. A, B, B, A, right? That goes here, and then this loop, and then B, and then A, and it's accepted, all right? So the NFA accepts A, B, B, A. Let's see, how can we derive that using the grammar? I'm trying to convince us that the grammar that we wrote there is actually equivalent to the NFA. I don't like this little thing here. Yeah. All right. Can we derive it? A, B, B, A. All right. Yes, we can. Of course, you start with S. Now, my strategy for making a derivation of that string is look at what you would have done on the NFA and then just choose the corresponding production in the grammar every time. So on the NFA, to do this, A, B, B, A, I go S to T, all right? And I'm going to choose the production that corresponds to that arrow. So first thing I'm going to do, S goes to AT, all right? Next on the NFA, in order to do A, B, B, A, you have to go here, and then this loop comes next. So I'm going to do that. T goes to BT. So this becomes A, B, T, right? You will see what you're doing if you do this. You are just sort of spelling out the letters one at a time in exactly the same way that you're going around the NFA. So the next NFA step would be T going to R. And so I use this transition, or this production, T goes to BR. So it's now A, B, B, R. Every time when I'm deciding what step to do next, I think about what would the NFA do? Next would be, I'm looking for this A right now, which corresponds to taking that edge. So that's R goes to S. So this becomes A, B, B, A, S. And then finally, I'm going to go S to T. A, B, B, A, T. And now T is my final destination. It's an accepting state, and so I can use the epsilon here. A, B, B, A, the end, all right? So I hope it's clear that any path in the NFA which ends in the accepting state can be achieved by doing those same arrows as the grammar productions, right? That's why this works. Yeah?
Can, instead of write epsilon and T, can I write S to A?
S to A? Just A?
Just
No, because then you can never get to T.
maybe R. Add an R.
Oh, S goes to AT or A? Yeah. I mean, that is equivalent as a grammar. I'm not sure what... it's not more efficient. I mean, because you're using more stuff over here. There are many different ways that you could write a grammar for the same thing. So, but I think This way is just a direct translation of the diagram. So I would assume that you're going to write it in that way. Right? How about I got another one to try. This is an interesting example. This is one of my favorite DFAs. This is the DFA that we talked about maybe in the first week of class. This is a DFA which takes a binary string and tells you if it's divisible by 3 or not. Remember that one? Or this is the accepting state at the beginning. It takes a binary string and reads it as a number and tells you if that number is divisible by 3 or not. Interestingly enough, you can do this with a grammar also. You can make a grammar which gives you all binary numbers which are divisible by 3. And how could you make such a grammar? Well, you just convert this diagram to a grammar. So I would give names to the states. I'll call them STR, might as well. And then just do, that thing that we just did. Every arrow on the diagram converts directly into a grammar production. See if you can work it out. Anybody want to tell me what should I say S goes to?
1T or 0S.
1T or 0S, yeah. And actually there's going to be one other thing that you get here.
Accepting the
Or the empty string, yeah. Because S is an accepting state. Great. 1T or 0S, yeah. How about T? Somebody else want to tell me what does T do? Yeah.
0R or 1S.
0R or 1S, yeah, great. And R. What do you think? Shout it out.
0T.
Yeah. 0T or 1R. Yeah, great. Welcome. The door is always open. Sometimes I close it. All right, yeah, so this is a grammar which can only produce binary numbers which are divisible by 3. I think that's kind of cute. Usually we think of grammars as creating strings like of text, but this is a grammar which kind of does something meaningful in terms of numbers. All right, excellent. So would you believe it if I turn this whole kind of construction into a theorem? It says every regular language can be generated by a grammar. All right? Every regular language can be generated by a grammar. Why is that? It's because every regular language has an NFA, and we just showed you how to convert an NFA into a grammar. So that means every language can have a grammar, all right? But, of course, we know there are some non-regular languages which have grammar. So in this sense, grammars are like more capable than than NFAs and DFAs. NFAs and DFAs can only do regular languages. Grammars can do regular languages plus some more stuff. Actually, a lot more stuff. All right? In fact, the grammars which generate a regular language can be made of a very specific format. Like as you noticed before, somebody asked about this. These grammars are very specific in that on the left side is always a single non-terminal. And on the right side, in each piece at least, always consists of one letter. That is a number in this example, but one letter followed by another non-terminal or an empty string, right? So there's actually a special name for that kind of very simple structure of a grammar, where everything on the left side is just a single non-terminal, and everything on the right side is just a single terminal together with a single non-terminal. That's called a single-step grammar. So actually, these regular languages can all be generated by what we call single step. I put it in quotes and underlined. Single step grammars. All right, and what that means is, so I'll put a little definition here. This is a specific type of grammar which has like a very specific structure to it. A grammar is single step when all productions look like either x goes to a y, where x and y are some non-terminals, or x goes to empty string, right? If you can write it using only productions of that form, of course joined together by the or symbol, then it's called single step. I'll say where x and y are non-terminal, and of course I will say perhaps x and y are the same. Like it is allowed to have x goes to ax, right? Perhaps x equals y. And a is terminal. It's one of the letters from our terminal alphabet. All right? That is called a single step grammar. They are very, very specific, very simple kinds of grammar. They don't allow any kind of funny business. All right. These grammars, they are ones which you can convert back into NFAs. So a single step grammar actually can be converted into an NFA. A single step grammar can be converted to NFA. That's because a single step grammar is going to make a regular language. And so it apparently you can make an NFA out of a single step grammar. So this is kind of the reverse process. How about this? I'll give you a single step grammar. Can you make it into a NFA? The answer is yes. You just have to kind of read it the same way that we were talking about, only in reverse. Y goes to AS or BX or epsilon. All right? So starting with this grammar, make that into an NFA. You just do the same procedure, only, the other way around. Anybody want to tell me how many states do you think we're going to have here in my NFA?
3.
Yeah, there's going to be 3 states. Do you got names for them? Yeah, we convert, remember when we did this the other way around, we convert every state became a non-terminal. This time we're just doing the opposite. So every non-terminal, that is the S, the X, and the Y, becomes a state. And apparently S is the starting state. S and X and Y. Are any of those accepting states? Yeah, the X and the Y, because we can see these going to epsilons will indicate that those are accepting states. So the X is accepting, the Y is accepting. And then we can just draw the arrows in. Each of these productions tells you how to draw an arrow. So when I see S goes to AX, that means there's an arrow from S to X with an A on it. S goes to BY means there's an arrow from S to Y with a B on it. And so on. You can just directly translate. X goes to AX means there's a looped edge here with an A. And then Y goes to AS, so that's like that. BX is like this. And epsilon means it's an accepting state. So that's the NFA for this language, all right? For this grammar. What kinds of strings are generated by this grammar? Well, you can try to answer that question by looking at the NFA, although I'm not sure it's very obvious by looking at that NFA, what is accepted and what is rejected. Maybe, is every string possible accepted? I don't think so. I think like BA is rejected. I'm not sure how easy it is. If you really wanted to be sure, I mean, this is maybe like that last question on the test. If I give you an NFA, it's often difficult to say exactly what the language of the NFA is. You could try to convert it to DFA, that might make it a little easier. I don't care that much though. All right? So if you have a single step grammar, you can always make a NFA out of it. Something a little fancier, slightly more complicated than a single step grammar is what we call, I'll say this is a bit fancier, is called a right linear grammar. There's all kinds of very specific classifications of different grammars which allow for increasingly weird funny business. A single step allows almost no funny business, or maybe no funny business. It's very, very rigid what kinds of things are allowed in a single step. What they call a right linear grammar is very slightly more complicated. It allows you to do slightly more complicated things. The only difference is instead of, so up here, every production in a single step has to have just one terminal here. A right linear is allowed to have more than one terminal letter here. So it can have a whole string. So a right linear grammar is one where all productions look like, I'll say, x goes to zy, where z is a terminal string, not just an individual letter, but a whole string. That's the difference between single step, which single step means they have to all be individual letters here. Right linear grammar means this thing can be a whole string, not necessarily a single letter. All right, or going to the empty string, as usual, or x goes to the empty string. All right, those are called right linear. The word right refers to the fact that this non-terminal is to the right of the string part. You could put it the other way around, and then that's called a left linear grammar. Although, for reasons we'll see, right linears are a little easier to make sense of. For example, here's an example of a right linear. How about S goes to A, B, A, S, or A, T? And T goes to A, T, or S, or epsilon. This is a right linear because every, it looks like a single step basically, but it allows for some extra letters in there, extra terminal letters. All right? Yes?
So some part of each production has to have the string and then non-terminal?
Every part actually has to have a string followed by a non-terminal or just going to the empty string. Like here, I mean that single letter, that is a string still. Or even here, this is just the empty string in front of it.
Okay.
Yeah. What is not allowed would be something like, you can't put or ASB. That's not allowed. That's no longer right linear because the non-terminal is not all the way to the right. Or you also can't have something like STS. You're not allowed to have several non-terminals. Those are not allowed. All right. A right linear, like this one, actually, this also can be easily converted into NFA. Let's see how we do that. A right linear, these also can be converted into NFA. And you do it kind of like a single step, only those single steps are whole strings. So for example, S and T are the basic strategy is still the same. I have two states called S and T, right? And S is the starting state. Because I see T goes to epsilon, that means T is the accepting state. Oh. T is an accepting state. And some of these arrows I can just translate directly just the way that I used to, just because some of them actually are single step. For instance, S goes to AT. That is a single step, and I can just put that arrow in directly. S goes to T with an A on it, right? And I see one other that I can put in immediately, which is T goes to S. How would I translate that into the diagram? Yeah?
Would it just be an epsilon?
Yeah, that's an epsilon transition from T to S. So that's like this. All right. What about the other ones? The other ones which are not single step, for example, T goes to AAT. What I want, I mean, basically what that means, don't write this down because this is slightly bogus, but it means that, right? If you're at T and you do AA, you can come back to T. Now, that's not allowed in an NFA. Anyone want to suggest how could I make that happen, but not writing that? Yeah.
Another state and then with A.
Yeah, we're going to sort of add a little dummy state here and do that, all right? So S and T are not going to be the only states in this diagram. There's going to be some extra ones which allow you to do these extra little steps. T going back to itself with a AA, all right? And then we also have, I've almost taken care of all of them. The last one is this, S goes to ABAS. I'm going to do the same thing here. Create some new states so that it can go to A, to B. It can do A, then a B, then a again, and end up back at where it started. Maybe I'll do them down here. Like this, A, B, A, right? That is how you do the S goes to ABAS. All right, it's pretty, I would say these are fairly easy constructions. You just have to kind of remember how to do it. I got one for you to try, if you will. How about, I give you a grammar, you create an NFA that corresponds to this grammar. S goes to ABS or BT. T goes to BBAS or AR. R goes to BS or ABT or epsilon. How about that? Make an NFA whose language is the same as this grammar. I'll give you a few moments. I'll do my answer here. I think I did it. Anybody get what I got? It's a little confused in there a little bit, but you have basically S, T, and R, and then S goes to ABS. I made this little loop here with another state. S goes to BT is just that arrow. T goes to BBAS. I had to make this little sort of detour here, BBA, and end up at S. All right. T goes to AR is this arrow. R goes to BS is that one. R goes to ABT is these two guys right here, or epsilon means R is accepting. Right? I hope you agree. Like I said, it's not a hard procedure. You just got to know how to do it. Any questions about that one? Something interesting about this construction is, I invented those. I guess I invented 4 more states which don't have names on my picture, which is fine. Not every state has to have a name. But if I give them names, maybe I'll call them X, Y, Z, W, like that. If you give them names, I can convert this back to a grammar, and it will be single step now. For instance, I will say, now convert that picture back to a grammar. It'll say S goes to AW, or I'm just looking at all the outgoing arrows from S, AW or BT. All right? And that's it. I think T, the outgoing arrows from T are BY or AR. And I think that's it. The outgoing arrows from R are AX or BS or epsilon, because R is accepting. And then we also have the XYZ. The X has an outgoing arrow BT. The Y goes to BZ. The Z goes to AS. The W goes to BS. Sorry, I'm off the bottom. Right? This is just converting that picture back into a grammar. But what's interesting about this is this grammar now is single step. All right? So this is a way, if you look at this, viewing that picture as kind of an intermediate step, what we did was take a right linear grammar and converted it into a single step grammar. And the way to do this is by making the NFA and then kind of unmaking the NFA and turning it back into a grammar. And actually, if you know what you're doing, you can do this procedure without drawing the NFA as an intermediate step, really. It's not very hard to do. So the moral of the story here is that any right linear can be converted into a single step. So actually, any right linear, if you want to, can be converted into a single step. Grammar, right? Which means actually the right linears are not any more powerful than the single step grammars, because you can always convert a right linear grammar back into a single step grammar. All right? These are all very kind of simple tricks that you can do with simple grammars. The linear or the single step grammars are very restricted in the kinds of things they can do. They can only do regular languages, and they can only look a certain way. They don't ever get much more complicated than that. Maybe I'll give you a little intro to what we're going to be talking about next time and for the next several times. The most important category of grammars that we're going to talk about, there's not really a lot to say about the single step, just because they're so restricted and so simple that there's not a whole lot to say about them. The most important category that we're going to talk about are what's called the context-free grammars. Context-free grammars, they have one restriction, but they still are capable of creating a lot of different kinds of languages. Context-free grammar, so I'll give you the definition first of all. A context-free grammar, these we're going to call CFG. A context-free grammar is one in which the left side of every production that is the arrows in the grammar, is a single non-terminal. All right? So I will just say it like, x goes to a, b, x, y. That would be allowed. That is allowed in a context-free grammar. All it is just the left side of the arrow is a single non-terminal. So this is allowed in a context-free grammar, but not something like ax goes to by, right? That is not context-free. Context-free means the left side is always just a single non-terminal. Maybe I'll just tell you what the terminology is supposed to indicate. Context-free versus, like, what does this have to do with context? Almost all the examples we've ever seen have been context-free. When you put other stuff on the left side, this you should regard as very weird, and we're usually not going to talk about grammars that do that because it's hard, very weird, and hard to analyze, really. But the idea behind a context-free grammar is, I'll say in a context-free grammar, the productions behave like substitution rules. I mean, in all grammars, that's what the productions are like. The productions are like substitution rules. All right, so if I see something like x goes to abx, this means x can become abx, right? That's what that means when you see a production like that in a grammar. Whereas in a non-context-free grammar, if you had something that was like ax goes to aby, what does that mean in terms of a substitution of x? It means something like, actually, if you look carefully at this, you could say, like, this a is here and here. All we're doing in this production is changing the x into by, right? But you can only do that if it's after a. That's what this rule means. If the x comes after a, then you can turn the x into by. So this rule means x can become by, but only in a particular, I'm going to use the C word, context. That's why the word context-free is used here, all right? X can become by. In a rule that looks like that, it means that x can be substituted and turned into something else, but only in a particular context. That is, only if it comes after a, all right? So context-free means you never have to consider the context. They're just like literal substitutions, and then you can make them whenever you want. That's why the word context-free is used for those languages. All right, we're going to talk much more about context-free languages next time. I think that'll do.